Good morning or good afternoon, good evening, whatever. This is a video on directions on how to calculate atomic masses and what an atomic mass is. The general information on elements is talked about in a different YouTube video and different information. So we're dealing with just the bottom piece. So by this time, you should have already printed out or opened up complete notes for isotopes and atomic mass calculation, which is, oops, it's not that. It's this. What I clicked on first was actually this, which is a blank page of the table we're going to use to do atomic mass calculations. And they're actually going to, on this one page that you print out, there are actually three places, so you can do 3 homework assignments on this one page. So, getting right to it, as we talked about in the other video, there is no such thing as an element. It's actually, each element is made up of actually a series of isotopes. Now, an isotope is an atom of the same element, but simply have a different mass. And the mass difference comes in the number of neutrons. And the way you can tell, and here's a little information, the way you can tell is the atomic number, which is in a periodic table. Each block is an element, and in each block there's a whole number, and that whole number is increasing one by one each block in series, in a line, or ordered. And that's called the atomic number, which is the number of protons. However, most periodic tables do not include the mass number, because the mass number indicates not only the number of protons, but it also indicates the number of neutrons. So it's a way of separating or identifying each isotope from each other. And since we're basically lying to everybody and telling everybody that this thing called an element is one thing, but it's in reality made up of many things, we really never like to advertise the mass number. So usually it's not on the periodic table. Again, it's the number of protons and neutrons. It's also, we also talked a lot in a different video about the symbolic representation. This one right here is the most common isotope symbolic representation. Mass number, atomic number. I gave you the mass, charge, and locations of the subatomic particle. But this video is all about determining how to calculate atomic mass. Well, there are actually 2 different definitions for atomic mass. The first one is, well, if we're lying to everybody and saying that this thing called an element, which doesn't exist, is only one thing, somebody's eventually going to ask, well, what's the mass of that one thing? Well, we need a mass. But we can't use any of the masses of the things that actually exist because there's more than one of them. So we need to take an average of it. And that average will be our fake mass of our fake thing called an element. So one of the definitions is it's the fake mass of the fake thing we call an element. The other definition is an explanation of the math that we do to figure this number out. And the definition is the weighted, and in parentheses, by the number of isotopes. That's the weighing factor, which is the number of isotopes. And that's a weighted average of the masses of all the isotopes in an element. So the atomic mass is the weighted by number of isotopes average of the masses of all the isotopes in an element. These things are extremely small and very light mass. So instead of having all kinds of scientific notation numbers, what they do is they have this unit called atomic mass units. There's actually a physical meaning to atomic mass units. I call it a fake unit because we're never going to really use that mass unit of AMU. We're going to, in the future, do some manipulations to make that unit go away in grams or kilograms come into existence. And so we'll do that later. So I call it a fake unit, even though it does have a physical meaning. And you can look and Google it and figure out the physical meaning. But I don't need you to really know that. Well, why is it that we can make pretend that one thing is actually make pretend that many things are just one thing. In essence, how can we take, for example, this is carbon. How can we take the carbon that has 3 isotopes and make pretend and tell everybody it's one thing and everybody will be okay with it? Well, I call it the M&M factor. M&Ms are bought in a bag, so that's the one thing. And everybody is okay with buying bags of M&Ms as long as there's 2 things. One, every M&M tastes exactly the same, which is true. Even though you have different colors, surfaces, they all taste the same. So the second thing you need is you need the same number ratio of all the M&Ms. In essence, every package you open has to statistically have the same number of yellows, greens, browns, reds. And they do. Maybe you've done this in math class, maybe you haven't, but they are. And you can Google it and you can see the statistics. So every time you open up an original brown M&M bag, there will be, statistically the same number and colors of M&Ms. And as long as we have that, we're okay with it. Because if I'm looking for a couple yellows and there's no yellows, I'm going to get pissed off. So as long as maybe there's not 3 yellows and there's only 2, but I'm okay if there's some yellows. So to make multiple things into one, you need those 2 things. And with atoms, you have it. With isotopes, you have it. Because every isotope has the same number of electrons. So chemically, they act the same. And this is why I talk about it, they all come in the same number ratio, which is called relative abundance. So if you look underneath, that's what this column is. So for carbon, 98.89% of the time it's carbon 12, and 1.1% of the time it's carbon 13. Well, there's a carbon 14. Yes, there is. But it's so few numbers that they don't even use it as a percentage, so we will only use 2. So this is the number of isotopes ratio. Okay, so what we are going to do is we need to take these percentages and change it into actual isotopes. So if you've been in an election recently, well, for me, 100% of my students say I'm the greatest teacher. Well, that's because they asked one student. So percentage doesn't mean anything until you make an assumption. That's why we have this assumption right here. So, and the most common number we use is 100, because 100 isotopes. Because when you assume 100, what what happens is all these percentages, you throw away the percent sign and you put the symbol or unit isotope. And the numbers don't change. If, however, you want to use one isotope, or then it would be 0.9889. Or if you don't like the fact it's 98.89 isotopes, ISO stands for isotopes, you can assume 10,000. So then that would be 9,889. It doesn't make a difference as long as the number here is brought down there. So that's how you're going to change all these percentages, and they become this column, which is the number of isotopes. Each row is a different isotope, and you show that by the isotope symbol. And what we have here is we have the actual mass of one isotope, so that's in AMUs per isotope. How do you get that information? You come down here and it tells you carbon-12 has a mass in AMUs, that's AMUs per one isotope of 12.00, and it has an abundance of 98.89, which means that each isotope of this isotope of carbon is 12.00 AMUs per isotope times 98.89 isotopes. And you want to multiply that together, you get the total mass of all those types of isotopes, carbon-12, in 100 isotopes, and that's the mass. And for significant figures, which we don't use significant figure rules in these calculations, you're going to keep 2 decimal places and lob the rest off. And then what you're going to do is you're going to do that again for each isotope you have. So sometimes you're going to have, you'll have more than 2 lines. Like you look at the blank, I only put 2 lines, blank copies. But if you have 3 or 4, you're going to have to squish them in between, because every row is another isotope. So once you have the masses of all the isotopes out of 100 isotopes, then you're going to add them all together to get the total mass of 100 isotopes, which you write there, and you write it back down here, and then you're going to divide it by how many isotopes you've actually assumed. In this case, you assumed 100 isotopes, so you divide it by 100. If you assumed 1, so you divide this by 1 isotope, or if it was 10,000, you divide it by 10,000 isotopes. And the resulting number, in this case, is 12.011 AMUs. And what that really means is 12.011 AMUs per isotope. And it's never any isotope, it's a representative isotope, because we're equating all the 3 different isotopes as the same things. And most of the time people just call it 12.011 AMUs. And that's what is called the atomic mass. And if you look on the periodic table, in each block, which is an element, the other number that's always there that's not whole is never whole. And that never whole number is always the atomic mass. So that's how you calculate the atomic mass using that table. And all the information you need is given to you. So all of this stuff is given to you, okay? And when you do the homework, you already have the answer, because your answer is these numbers, which are the atomic masses. Okay? I hope that helps in calculating the atomic mass. Thank you.